Alright, welcome back to 4.3 double integrals over general regions. Last time, or in 4.1, I'd say, we did double integrals, but we didn't do them over we didn't do them over any region, we just did them over a rectangle, right? In 1D, you don't really have the notion of integrating over a region that isn't anything other than just a line, because it's only one dimension like that, right? But in 2D, we've already discussed that the domain of a function can be any shape. It can be a circle, it can be a rectangle like we did in 4.1, or it can be a triangle, it can be some wacky shape that the domain that we want to focus on can exist in. So, for example, in this question right here, your area that you want to integrate, C for circle, C for circle, is it's a circle and it has radius 2, right? So the integration will look something like this. So this is the shape C, and if you draw a circle, which I can draw, there you go, and then you highlight in the circle, that is the region of integration. And we've learned in 4.2 that what you can do here is you can actually compute the Jacobian of polar coordinates to make to make it so that it's a lot easier to integrate. So how are we going to integrate this? Well, the Jacobian for dA. So first of all, I'm gonna write it down. So C 4 minus x squared minus y squared dA is equal to the double integral. I'm gonna leave some gaps to put my r bounds and my theta bounds. 4 minus r squared, because this is 4 minus x squared plus y squared. So 4 minus r squared times r dr d theta, because that is the Jacobian for dA, for polar coordinates for dA. It's dA turned into r dr d theta. Now, what are we taking the integral of? So how much, what's the radius? What's the amount of radius that we have to sum up for this shape? So unlike x and y coordinates, we can't go up and down. We can't go up and down. We can't go left and right. Right? Up and down and left and right doesn't work. It's like when we integrated -1 to 1, -1 to 1 dx dy, we could go from -1 to 1 on x, and then -1 to 1 on y. However, in polar coordinates, that doesn't happen. What happens is we go from the pole, or the center, or the origin, to whatever radius we want to integrate at, and the radius is constant in this entire shape. So what does the radius start at? The radius starts at 0, and the radius ends at the circumference of the circle, which is 2. So the radius, we have to add up all the radii from 0 to 2, or all the little changes that makes that radii from 0 to 2. Now what about theta? So theta equals 0 starts here. So if we move a little bit of theta, that's d theta. So what are all of the d thetas that we have to add to? We have to add the d theta from 0, theta equals 0, all the way around the circle, which means we have to add all these, all these little slices, right? All of these little slices, we have to add them all around the circle, which is 2 pi radians. 2 pi radians. Now we're gonna calculate this. I'm just gonna calculate it real quick. You should already know how to do it, but it should be 8 pi. So let's calculate it. This is equal to 0 to 2 pi, the integral from 0 to 2 of 4r minus r cubed dr d theta, which is equal to the integral from 0 to 2 pi of 2r squared minus r to the 4th over 4, bounded from 0 to 2, d theta, which is equal to the integral from 0 to 2 pi of 4d theta, which is 8 pi. So yes, it does evaluate to 8 pi. There you go. It evaluates to 8 pi, which is great. We did something right. So that means that the area under the surface, 4 minus x squared minus y squared, which is a paraboloid. Or the volume. I'm sorry, not the area. So what you're getting is something like this, something like this, something like this, something like this. Oh, that's not a very good drawing. Like that, like that, like that, like that. So the area of this right here, or the volume, I'm sorry, the volume of that right there is 8 pi. Now, if we were to evaluate this from -2 to 2 and from -2 to 2, we would not get a circular region. In fact, what we'd get is we'd get a rectangular region. And if we get a rectangular region like this, we'd have to count the negative, let me draw it. We have to count this negative section as well, because it's under the xy plane. So you have to count negative volume and positive volume as well. We don't want to do that. So that's why that's why most of the time when we have these types of nice areas, we would just use the circular regions rather than the rectangular regions, which include both negative and positive slices. So before I continue, I have to explain two terminology: type 1 region, also known as Y simple, and type 2 region, which is also known as X simple. So what is a Y simple region? A Y simple region is a region that can be expressed, that like its boundaries are two y equals functions. They are not two functions of y. I said that many times the last time. I've said it so many times last time that I have to scrap that video and make a new video right now. So it's not two functions of y. It's between two functions of x in this case, and in the 3D case it will be functions of x and z. But it's two y equals functions. So y equals to y, from y equals bottom bound to y equals top bound. That's a type 1 region. That's what we usually call a function. And then the type 2 region, right? So it's like this. A type 2 region, I don't know why I have these red lines here, but type 1 regions go from bottom to top, and they are y equals functions. Type 2 regions go from bottom or left to right, I'm sorry, and they are two x equals functions. So what you'd end up is, if you set it in terms of this, you are like a lot more likely to have dy dx. So functions f of x, y, dy dx. And for this situation, you will have dx first, then dy. So why would you have why would we have dy dx first? Well, because we have to take this y equals function, we have to evaluate the y equals from the bottom to the y equals from the top. Now, if we did dx first here, we'd have to switch the y and the x to get x is equal to a function of y, and that would just not be very nice with these right here. That's probably why I put them here. So these are things that make them not functions, right? That's why it's called y simple and it isn't called x simple, is because if you go from left to right, you bump into one x, it's not simple. It can't be expressed into a simple double integral, because when you bump into one x and then you have to discard this region, like you have to discount this and you have to do another double integral, and yet you bump into another x, discard the region, bump into include this region, discard this, include this, and it's very annoying. And that's why it's called a x or a y simple region, because we can express it simply in terms of two y equals functions, and that's why dy has to be first, because we will find all of the y formulas first, all the formulas for the length of this y, or the area of this y, or of these lines that are from f1 to f2 long, so it'll look something like f1 to f2, and then we will sum all of the lines when we go from left to right. Same thing for this one. We'll sum all of the lines when you go from up to down. It's very simple summing up all the lines because it's not one boundary and another boundary. It's not like two different boundaries like that. That would be very crazy. That would not be y simple or x simple, and that would just be very hard to set up, and I wouldn't want to set that up. So yeah, it's very simple in the x direction, because once you've taken all the slices, you can just add them all from C to D, and that will get you, so this will be like from G1 to G2. And putting G here is probably not a very good choice, but whatever. So in 1D we have this. So yeah, I've already explained this, but in 1D we can do this. We can do the area is equal to this top area, because this top thing evaluates the area under the curve for y equals x from 0 to 1. From 0 to 1, right? We find the intersections, so we know that it's 0 to 1. And then after that, we can just subtract this area right here, because this area is the area under the curve of y squared. And then what we'd be left with is this d section right here, which is 1/6. So how do you use a double integral to do this? You can use a double integral to do this. And last time I said that double integrals aren't just to find volume. They can also be found area if the inside is 1. And usually I just write it like this, dA, like that, right? With nothing in the center, because we're just summing up all of the areas. Right, putting a 1 in there might be a little bit confusing, but without the 1, we just know that we're summing up all of the areas in y and all of the areas in x. So is this an x simple or a y simple region? I'll give you 2 seconds to answer. 2, 1. All right, you guys are correct and wrong, because it's both. It's both x simple and y simple. Well, which one should I use? Well, they gave you the functions, or I gave you the functions, so you should use the functions that I gave you, which is the integral dy dx, right? I'm setting this as if it was a y simple region, even though it can be expressed as an x or a y simple. You could do, this is x is equal to square root y, this is x is equal to y, and then you could do from y to square root y. That works as well. But we want to express it in terms of y. If we want to express it like it was a y simple region, then we'd have to go from the bottom function to the top function, right? I'm showing these small slices because we're adding up all of the y's from x squared to x to get this line, x squared to x, to get the length of this line right here, the red line and the red and blue lines. We're adding up all of the y's, and then we just have to add up all of those lines from 0 to 1. So that will be 0 to 1, right? All of the lines from left to right from 0 to 1. First of all, we add up all of the lengths from the bottom function to the top function to get those lengths of the lines, and then we add all of those lines from left to right to get the area of the region. And what will that give you? That will give you, well, that's equal to 0 to 1 of y evaluated from x squared to x dx, which is equal to the integral from 0 to 1 of x minus x squared dx, and that gives you the exact same answer, right? So you might say that this is a little bit of a stretch, it's a little bit harder to evaluate it like this, but once we get to more complicated regions, you will see why this is a better method. And also, it's also just a better method if you want to find the volume under the surface, or the mass of a plate, a 2D plate, flat plate. Alright, anyways, so find a volume under the surface above the region bounded by x equals 0 and x equals 4 y squared. So we have g of xy is equal to that, right? So the double integral of the region, I would use h for hemicircle or s for semicircle, because this is a semicircle. But I'm going to use s for semicircle, sure, dA. And what's the region S look like? Well, x equals 0 is what? Is the y-axis. So that's very easy. And then what's x equals 4 minus y squared? Well, y equals 4 minus x squared is a parabola pointing down, like this, opening down. That's shifted 4 up. So x equals 4 minus y squared is basically the same thing. It's just, instead of in the y direction, pointing the negative y direction, it's pointing in the negative x direction. So it becomes something like this. Right? So it's pointing in the negative x direction. I'm going to shade the region, which is this region right here. It's bounded by this region. Pretty nice region. Alright, so is this x simple or y simple? Okay, this is actually not both anymore. Well, first of all, they gave you two functions, so I would just do dx dy anyways. But, yeah, it's not both. It's not a question of being both anymore, because, or actually, I would say it's still both. It's still both. You can do, this is two functions, right? In this case, it's a single function, but you can actually separate this into two functions. What you'd get is this is y is equal to square root of 4 minus x squared, and then y is equal to negative square root of 4 minus x squared. Now, just by looking at this, you probably already figured out why I don't want to do this. I don't want to integrate like this. This is tragic. I definitely do not want to integrate like this. So what we're going to do is we're going to integrate x simple as two functions of x. So that's equal to the integral of dx dy of x over y. And what do we have? We have this. We have the low x, we have to integrate from the lowest x, which is 0, right? 0 to 4 minus y squared. That's called a representative slice. So we integrate from the lowest s to the highest x. It's sliced just to make us recognize what we're integrating. Now, what about this? What about the x's? What's our bounds for the x's? How do we know our bounds? Or how do we know our bounds for the y's? I'm sorry. So, like, how do we know our bounds for how much we're supposed to add up? What we're supposed to add up? So, the way that we know our bounds, we have to solve an equation. So, it's 4 minus y squared is equal to 0, which means 2 minus y times 2 plus y is equal to 0, which means y is plus or minus 2. So those are our bounds. Our bound is from, we have to integrate from negative 2 to 2 to get all of those, all of that yellow goodness, all of the special y values. Alright, let's integrate. So first of all, we integrate with dx. So that will be negative 2 to 2 of x squared over 2. And I'm going to factor y out because y is a constant in this case when we're integrating with x. 0 to 4 minus y squared dy, which is equal to negative 2 to 2 of 4 minus, or I'm going to put 1/2 outside now, actually, because this x squared over 2 is annoying. So 4 minus y squared, 1 over y times 4 minus y squared squared, dy, which is equal to 1/2 times the integral from negative 2 to 2 of 16 over y minus 8, 8y, I think, 8y, yes, and then plus y to the third power, dy, which is equal to 1/2 times natural log, or I'm sorry, 1/2 times 16 natural log of y. Alright, I need to move this. Alright, this is really annoying. Make this smaller. Keep going. 1/2 times 16 natural log of y multiplied by 4 natural log of, or minus, I'm sorry, 4y squared plus y to 4th over 4. Evaluated from negative 2 to 2. Which is equal to 16 natural log of 2 minus 16 plus 4 minus 16 natural log of negative 2 minus 16 plus 4. So you end up realizing that all of this just evaluates to 0. Because this cancels out, this minus 16 minus 16 cancels out, 4 minus 4 cancels out. So all of that work just for the answer of 0. A little bit disappointing, but that is the way it works in this in this predicament, I guess. Anyways, let's continue. Evaluate this if D is the region bounded by this. So this is the exact same region as the example that I gave you, which is this and then this, right? So it's a very simple region from here to here, and this might actually be a little bit annoying to evaluate, but we will see. So this is y equals x, this y is x squared, right? So we have an integral, we have an integrand now. So x to x squared divided by and 0 to 1 is what we decided. So it's dy dx, because 2y equals functions, and then 4 minus x minus 2y. So let's evaluate. This is equal to, you guys can try this yourself actually, so try it yourself. I'll give you 3 seconds, pause the video if you need more than that, and the 3 seconds have ended, so I will now try it and do it really quick so you guys can check your answers. So 0 to 1 of 4y minus xy minus y squared evaluated from x to x squared, which is, this is dx, which is equal to 0 to 1 of 4x squared minus x cubed minus x to the 4th minus 4x minus x squared minus x squared dx, which is equal to the integral from 0 to 1 of negative 4x, or I'll put minus 4x here, minus x to the 4th here, minus x to the 3rd here, and we have 4x squared minus 2 negative x squared, so it becomes positive, so it's just plus 2x squared. Hope I didn't do anything wrong. That would be embarrassing if I did. So, or I'm sorry, this is minus 2x squared, minus 2x squared. Alright, dx. No, it is, no, it's 6. No, it's 6x squared, plus 6x squared. There you go. 4x squared plus x squared plus x squared, dx. Which is equal to what? Which is equal to negative x to the 5th over 5 minus x to the 4th over 4 plus 6x, or 2x cubed, I'd say, minus 2x squared, minus 2x squared from 0 to 1, which is negative 1/5 minus 1/4. That should be the answer. I hope I'm not wrong. But that's a pretty low number because we evaluated pretty close to 0 to 1. So that's what happens, I guess. It's a plane, so the numbers will be pretty like fractiony. It'll be pretty nice, I'd say, but it won't be very I wouldn't say nice. It's still pretty nice, but it will be pretty boring, pretty geometric. Find the volume under this. Alright, this is not boring. This is definitely not boring. Find the volume under this weird surface, whatever it is. Above the region y equals 0, y equals sine x, and this. Alright, so it kind of already gave me the region, so I'm just going to say that this is D. The region D is y equals 0, y equals sine x, which looks like this, and then the x's are evaluated from 0 to 2 pi over 3. So sine of pi is 0, so 2 pi over 3 is smaller than pi, so it looks something like right here. So it's this region right here. This region. Alright, I'll have you guys try it, and you guys can pause right now. I will write the integral out, and then I will start trying it. So you have that much time, unless you guys pause. Right, so first stop we're going to evaluate dy first before dx, because this is actually a y simple region now. It's no longer an x simple region, because if we evaluate x first, we're going to hit our own function, and that's very annoying. So this is equal to the double integral, or the iterated integral from cosine x sine y still dy dx, but it's 0 to sine x, and 0 to 2 pi over 3, because that's what it gave us. So this is equal to the integral, or the integral from 0 to 2 pi over 3. So sine y, the derivative, or no, not the derivative, the integral of sine y is negative cosine y. So cosine x, negative cosine y, evaluated from 0 to sine x dx, I think. And this is equal to the integral from 0 to 2 pi over 3 of, let me shrink this down. Cosine x, if you add sine x, it's just sine x, right? So cosine x, I'm going to put the negative outside because this is really annoying. Cosine of sine x minus cosine of 0, which is 1 dx. So what does this give us? This gives us the integral from 0 to 2 pi over 3 of, I'm going to actually put the negative outside, is equal to this cosine x, cosine of sine x, minus cosine x, or yeah, minus cosine x dx, which is equal to, well, this is a little bit hard to evaluate unless you figured out how to evaluate this. Is a little bit hard to evaluate. So the integral of sine x is cosine x dx. So you could do a u substitution. U is equal to sine x, or you could do just figure it out through reverse chain rule methods, that this evaluates just to sine of sine x. So negative sine of sine x, right? So if you take the derivative of this, you'll get cosine of sine x times the derivative of the inside, which is cosine x, minus sine x. Evaluated from 0 to 2 pi over 3. What is sine of 0? It's 0. What is sine of 2 pi over 3? Sine of 2 pi over 3 is exactly root 3 over 2. Negative sine of root 3 over 2 minus root 3 over 2. And this actually becomes a plus because we have a negative on the outside. It has to distribute to both elements. So that's a pretty interesting integral that we got there. It probably won't be very interesting in your test. In fact, this next slide will probably be a little bit more useful. Changing variables. How do we change the bounds when a region is maybe both x and y simple, or maybe not even both x and y simple? You're just made to change the bounds. So this is how you do it. You have to draw the region. So we want to change the bounds in this integral. We draw the region. This is y equals negative x and y equals negative 2. So it's probably not a good idea to just draw the first quadrant. We have to draw this instead. Y equals negative x and y equals negative 2. So the region looks something like this, right? And we just have to check, does x go from 0 to 2? No, it doesn't, because this is the wrong integral. X is supposed to go from negative 2 to 0. Negative 2 to 0. Now this is the right integral. So from negative 2 to 0, you go from here all the way up there. So this is the region right here. It's bounded by y equals negative 2, y equals negative x, and x equals 0. Y-axis. So that's the region. Now we have to analyze the slices. So dy means y equals negative x and y equals negative 2. Means we're adding or we're making lines that are horizontal. Or no, I'm sorry, not horizontal. Y equals negative x to y equals negative 2 to y equals negative x. So that's vertical. Y means vertical, not horizontal. So we're making these vertical slices. We're adding up all of the different changes in y from the bottom to the top. So we want to change. If we want to change the bounds, we have to stop that, and we have to add all of the slices from left to right now. And we also have to make them in terms of x, right? So how's that gonna work? Well, let's see. Y is equal. Okay, so x is equal to. So this slice right here, this region right here, or this line is x equals 0. It's the y-axis. What's the line of this? Well, if it's y is equal to negative x, then it's also x is equal to negative y. So x equals negative y is this line right here. So it goes from 0 to negative y. Right? 0 to negative y. Pretty simple. Now we just got to add all of the x's. So this is the x, and now we just got to add all the y values. So what are the y values? The y values go from under here, negative 2 to negative 2 to 0. So I'm sorry, this is wrong. When I had it originally, it was right. So 0 to 2. Negative 2 to 0. So we're adding up, when we have all of these slices here, we're adding up all of the slices from the bottom to the top. Like this. To make this triangle. Useless slice. Okay, so let's change the bounds in this integral. Let's make the shape. This is x equals negative y, which is y equals x squared. But it's only the positive part of it, so y equals x squared right here. X equals negative y. X equals 2, which is something like this. Or no, it's not something like that. I'm sorry. It's something like this. I get so used to having x as left or right that I forgot that x equals 2 is a line where y can be free. But the x has to be a fixed number. So this is the region that we're talking about. Why do I know? Because, well, the y's from 0 to 4, we can pitch x squared. Or well, we can actually just pitch, this is 2, so y equals 2 squared, y equals 4. So it hits, the two lines hit at y equals 4. So we want to change the bounds, dy, dx. This integral is actually impossible if you don't change the bounds. So x cubed. So what line does it hit first? Well, it hits, the bottom line is 0. Y equals 0. It's right here. Y equals 0. And then what's the top line? It's y equals x squared. What's the bottom line? Or what's the bottom value for x is 0. And what's the top value for x is this line right here. It's 2. So if we evaluate this with respect to y, there's no y in here. So we could just put a y, make up a y. It's like evaluating a constant. So 3 cosine of x cubed y from 0 to x squared dx, which is 0 to 2 of 3 cosine of x cubed times x squared dx. And you realize that by doing the reverse chain rule, it's super nice because the derivative of x squared, x cubed is exactly 3x squared. So this is equal to sine of x cubed. Take the derivative of that, you get cosine of x cubed times the derivative to be inside, 3x squared. And that's why 3x squared is so nice. Evaluated from 0 to 2, which is sine of 8 minus sine of 0. Sine of 0 is 0, so sine of 8 is the answer. Very nice integral. I could have made it nastier, but this is just the main exercises from changing the bounds to go from bottom to top rather than left to right with the x symbol. So we want to go from bottom to top with a y symbol. Polar integration is the last topic. This video is getting quite long. So polar integration in general regions, we do the exact same thing, but with r and theta basically. Now, usually what we do is we don't have functions in terms of theta. We only have functions in terms of r. And in fact, that's all I'm going to show, because having functions in terms of theta is going to be very, very nasty, because theta can be infinite. Theta doesn't have a stopping point. Theta can roll over to that same point again and again and again, and it's very annoying. So that's what I'm not going to focus on. Find the area of the region between these functions using double integrals. So obviously you can just not use double integrals, but we're going to use them because we are calculus students, not algebra students or geometry students. So the first circle will look something like this, and then the second circle will look something like this. Alright, I drew it very well until I got to the end. There you go, something like that. Y equals x. And y equals 0. Now, I didn't actually specify this enough. It feels like, yeah, I didn't specify this enough. We're just going to calculate it in the first quadrant, alright? We're going to calculate the region in the first quadrant, because if it's bounded by these four, it can be this region, or it can be this region, or it can be both. If it was both, you just double it. But on the test, I'd probably write a better integral, better way, phrase the question better. But we are just evaluating that. So, or I'm sorry, it's y equals 0, so I drew the wrong thing anyways. Y equals 0 is the x-axis. So it's this one, not the other one, because it's, by default, I am going to use the first quadrant. So this one. Alright. So I've already told you that what we're going to try to do first is we're going to try to have our two functions of r. So r d theta. We're going to have functions of r first before functions of theta. So it'll rarely be d theta dr. Sometimes it might be d theta dr, but most of the times it'll be r dr d theta. So two functions of r, which means we have to take the lowest r and we have to go to the highest r. So what's the lowest r here? The lowest r here is, well, x squared plus y squared is 4, so r squared is 4, so r is 2. And x squared plus y squared is 9, so r squared is 9, so r is 3. So lowest r is 2, highest r is 3. Right, and this is gonna be like this. It's not gonna be, there's nothing inside because it's the area of the region. Now, what about our thetas? Our thetas start from 0. This is the 0 line. But what's this line? That's actually a little bit hard to figure out, right? But what we can, with one of our functions that we have, one of our kind of rules that we have for what theta is, tan of theta is y over x for in polar. That's one of the rules that we have for polar. Tan of theta is y over x. So if we just made this y over x is equal to 1, then that's what we're going to get. We're going to get tan theta is 1. In fact, if we had y equals mx, or any line like this, then y over x is equal to m, so tan theta would just be equal to m. Tan theta is equal to 1. Theta in the first quadrant is pi over 4. So that is our upper bound for the angle. So the bottom bound is 0, top bound is pi over 4. So whatever we have, we're just going to multiply with pi over 4. I don't know if you guys remember Fubini's theorem. I don't know if I even told you this. But with a function like this, what you can do is you can separate them into two integrals like this and evaluate it a lot quicker. This is called a separable function because you can separate them into one function of just r and one function of just theta, right? It only works with rectangular bounds. So I'm going to call this rectangular even though it's a slice of a pizza because there are constants on the bounds. So if the bounds are constant and the function separable inside the integrand, you can separate the two functions like this. So what are you going to get? You're going to get r squared over 2, evaluated from 2 to 3, times, you're going to get pi over 4, minus 0. This is equal to 9 squared, 81 over 2 minus, no, 9 over 2, I'm sorry, minus 4 over 2, which is 5 over 2, times pi over 4, or 5 over 8 pi. You can evaluate this some other way. Like, you can just take 1/8 times 3 pi, or 3 pi 3 squared minus pi 2 squared. That works as well, but this is just a way you can do it in polar, and it will be more useful when we have something inside that makes us find the volume under the surface, like this one. This is hard. This question's a little bit hard if you don't think about it. So z is equal to 4 minus x to the 4th minus x squared y squared minus y to the 4th. And it's even harder when you don't make the question right. This is the question. 2x squared y squared. I checked in my notebook, and this is the actual question. So 2x squared y squared. Fix your question, because this is the right question, not the one with x squared y squared. That's impossible. So let's try. Let's see if we can find the answer. So it already gave us this, right? If you see this, it's automatically going to be polar. How though? How are we going to change this into polar? There's actually a very neat trick, right? If you see x squared plus y squared like this, you're pretty sure it's going to be polar. When you see polar stuff like this, it's definitely going to be polar, because changing polar to rectangular, that is a whole other mess. It is really annoying, and you definitely would not want to do that. So that's z is equal to 4 minus this. What's this? This is actually an application of a plus b all squared is a squared plus 2ab plus b squared. So if you figure that out, then you realize that this is x squared plus y squared all inside a negative, or all going to be multiplied by a negative, which is a very neat trick, because this just actually really simply simplifies to 4 minus r squared squared, which is 4 minus r to the 4th. So that's our integrand, 4 minus r to the 4th. D times r dr d theta. But what's our region of integration? Our region of integration is this crap. 2 cosine 2 theta. What does that mean? What does 2 cosine 2 theta mean? We're actually going to have to draw the region. We're going to have to graph the region. So when theta is equal to 0, we get r is equal to 2. So something like this. When theta is equal to pi over 3, let's say. So when theta is equal to pi over, or no, not pi over 3, pi over 6, we'll get 2 cosine of pi over 3. Cosine pi over 3 is 1/2. So when theta is pi over 6, like this, it'll look something like this. And then when theta is pi over 4, so something like this. Right, so when theta is pi over 4, something like this, we get 2 cosine pi over 2. Cosine pi over 2 is 0, so it's just like right here. Right, and if we go the other direction, what you'd actually find out is, well, if we keep graphing, what you'd actually find out is the graph looks something like this. If I can draw it. It looks something like that. That's what the graph looks like. But we only want one petal, so how are we going to do that? Well, one petal, this is half a petal. We can't just double it, but this right here is already half of a petal. So how do you get the other half? We reverse it. We're going to go the other way round. So what's the other way round? The other way round is, this is theta equals 0, and this is theta pi over 4. So if we go the other way round, we're going negative. We're going back in time, back in angle. So this is also theta equals, right here, theta equals negative pi over 4. So our lowest theta is not 0. It's theta equals negative pi over 4. And then as the theta gets bigger, it hits 0. It'll encompass half of the area. And then when it gets back to the center, it will encompass the entire area. So this is the region of integration. And our thetas go from negative pi over 4 to pi over 4. What does our r go? Our r goes from the center to the function, right? Our center to the function. So it goes from theta 0 to, from r equals 0 to r equals negative pi over 4, or r when theta is equal to negative pi over 4, and then it goes to the function. It shoots out rays that go from 0 and it hits the function. So our r starts from 0 to the function, 2 cosine of 2 theta. And this is going to be very, very messy, and I'm actually not going to do this. There's no way I'm going to be able to get this done in a sane amount of time, because it has cosine to the 5th in it. But if you guys want to do it and tell me what the answer is, I'll pin your comment in the description. So this is equal to negative pi over 4 to pi over 4 of 4r, so that's 2r squared, minus r to the 6 over 6, evaluated from 0 to 2 cosine 2 theta d theta. This is equal to negative pi over 4 to pi over 4. And if you put this in, you will get a mess. You will get 2 times 2 squared cosine squared of 2 theta minus 2 to the 6 cosine to the 6th of 2 theta over 6 c theta. It might evaluate to 0, honestly, but we will have to see what happens. If you tell me the right answer on the with supporting work in the description, I will pin the comment. So that's going to be it for this lesson about general regions. Next time we're going to go to triple integrals, which will be a lot more exciting than this. But until then, I will see you next time.